So the learning objective for this lesson is to describe solubility. Now, before we can actually get into the nitty-gritty of actually why we're actually getting things dissolved, we need to understand this idea of a polar molecule. And the great example of a polar molecule is our good old favorite H2O. Now, as we know, H2O creates this little molecule, which we've seen before, this bound together with covalent bonds. But it doesn't actually take this perfect little neat shape. What it actually does is it actually forms into this awkward little sort of boomerang shape. And what that means is we get an uneven charge distribution. So we have a more positive end down the bottom where you've got those protons in the hydrogen nucleus, and all those electrons are in the upper near the oxygen. So you've got uneven charge distribution. So because of that boomerang shape, we get that distribution of charge that's uneven, and this produces strong positive and negative poles. Those negative and positive poles can overcome the ionic bonds in molecules and split them back into their ions. So it's often a lot stronger, those poles, than the attraction of ions in an ionic bond. So let's take a classic little molecule here, sodium chloride, NaCl. What happens is it goes into the water, and those polar molecules, the water, it separates NaCl into its two positive and negative ions. And when it does this, we say it has dissolved. So we can no longer see the NaCl molecule anymore. It's now dissolved into its ions, and we write this. The nomenclature we're going to start introducing now here is NaCl, and you see we've got a little S, and Na plus, we've got an AQ there, which is short for aqueous. We're going to write this down in a second, and a chlorine, which is a positive ion, and it's also aqueous. So using this example, we are going to check out this new nomenclature that we're looking at. S stands for solid, aqueous is the AQ, which means it's dissolved in water, and G is gas, which means it exists in the form of a gas, obviously. That G one's going to be less important for us, looking at precipitation reactions. For us, we're going to be focusing a lot more on the S and the AQ. Now, there's a bit of terminology we have to talk about when we're talking about precipitations, which is where this is all leading to with our solubility. So first word we're looking at here is dissolve. Obviously it's a word we use quite commonly. It's when a solid becomes incorporated into a liquid.
How about a little fire, Scarecrow? You cursed brat! Look what you've done! I'm melting! Melting! Oh, what a world! What a world! Who would have thought a good little girl like you could destroy my beautiful wickedness? Ah, look out! Look out! I'm going!
I feel like the more appropriate terminology here would be dissolving.
I'm dissolving! Dissolving! Oh, what a world! What a world!
Yeah, it doesn't quite have the same ring to it, but I guess the producers had to make a choice. Next is our solute. That's the solid that does dissolve. So in the example we previously used, NaCl, sodium chloride would have been our solute. The solvent is the liquid that the solute dissolves in. In our case, that was water, and in most cases, a lot of the cases, it is water that it's dissolving in. The solution is the liquid mixture in which the solute is evenly distributed within the solvent. So once we've got a solute that is dissolved into the solvent, we now call that a solution. Another term we use is soluble. That means it is able to be dissolved. Another term is insoluble, obviously not able to be dissolved. Now, how we determine what compounds are soluble and which ones are insoluble, well, unfortunately there's a bunch of rules here that govern this, and fortunately we write these all down in a table. So we've got obviously two columns here, soluble and insoluble. Now, to do this properly, you're going to need to have a copy of your periodic table. So first, compounds that are soluble, so they will dissolve, are our group 1 and ammonia. So group 1 here is starting at hydrogen, going down. That's our group 1. So any ionic compound where it's got lithium, sodium, potassium, rubidium, they're all going to be soluble, and ammonia. If your compound has a nitrate in it, that's going to be soluble. All acetates. Now, we get chlorides, bromides, and iodides, with exceptions. So if you've got, let's say, beryllium chloride. Cool, beryllium says chloride there, so that is soluble. But if you get silver bromide, silver chloride, no good. It's going to be an insoluble one. Sulfates are all soluble, with exceptions: silver, lead, barium, strontium, and calcium. Now we have our column for insoluble. So all carbonates are insoluble, with exceptions, of course, the group 1s and ammonia, which makes sense because we know that they are soluble from the previous column. And that same exception applies to sulfites and phosphates. So all carbon, sulfites, and phosphates are insoluble except group 1s and ammonia. All hydroxides are insoluble, with exceptions: group 1, ammonia, and barium, strontium, and calcium. And the same exception applies to the oxides. Sulfides are all insoluble except groups 1 and 2 and ammonia. So, using this list of solubility, and you should definitely take a moment to pause this video and write those down, because you're going to need to use this as a reference to complete your quiz, which will essentially be looking at different compounds and determining whether they're soluble or insoluble.